All right, everybody, this is an example of a kind of an easier conservation of energy problem. So we have a skier sliding down an icy hill from rest at an initial height of 30 meters. And they say the friction along the icy hill can be ignored, but at the bottom, the friction becomes noticeable as they're sliding along the flats. So there's a couple kinds of questions we could ask. A simpler one would be, if you know the height of the hill, calculate the speed at the bottom. It's kind of like a classic roller coaster problem. But then B, how far does a skier glide along the flats at the bottom of the hill? So now at the bottom of the hill, um, here between B and C, we've got friction, so there'll be work done by an external force. And so how can we work with these ideas? You can see that if we take a look starting from the top here at A and watch the energy bars, we're starting with all potential energy because we're starting from rest. It's becoming more and more kinetic energy as we go down the hill. At the bottom, it's all kinetic energy. Okay, and then as we slide along the snow, that kinetic energy is turning into work done by an external force, and all of our total mechanical energy is turning into heat. So let's take a look at how we can get our mind around this kind of problem. All right, so we've kind of done a diagram. Bar charts kind of help. They help us think about what's happening. Ignore these values right here. I chose some different numbers, I guess, to do this problem. So in any case, what we do is I like to make kind of a T-chart that talks about the energies at point A and the energies at point B. Since I know my total mechanical energy at A should equal my total mechanical energy at B, right, I could usually set the sum of these two columns equal to each other. So I like to ask myself of my mechanical energy, what are my forms at point A and what are my forms at point B? Do I have kinetic energy at point A? Do I have potential energy of gravity at point A? Do I have any springs like elastic energy at point A? So, if I take a look at the context of this problem, we're starting from rest, so there'd be no kinetic energy. We're at a height above the ground, so we do have potential energy. And there's no springs in the problem, so there's no energy there. Then I'll take a look at point B, and I realize at point B I will have kinetic energy, but I have no height left, so there's no potential energy there. And I have no springs that I've compressed or stretched, so there's no energy there. Now the other thing I would have to ask myself, would there be any work being done by an external force? And in this case, since it's an icy hill and nobody's giving a push or a pull, there would be no work done by the external force. So there'd be 0 joules lost or gained there as well. Okay, so as I go over and take a look at my total mechanical energy, I can just put in zeros. I have kinetic plus potential plus the other potential plus the work. And then on the other side, I just have my kinetic and potential energy terms. And then my, I have zeros in my column here for my total mechanical energy at A, except for potential energy. And then at point B, all I had was kinetic energy. So I can set those two equal to each other and then solve, realizing that the mass cancels out. I can solve for the velocity at point B. And if I put in 2 times 9.8, times the height I started at, 30 meters, I get a final velocity of 24.2 meters per second then at that point. So that's just a potential energy to kinetic energy type problem. So what about the problem where we want to find out how far we're going to slide along the bottom of the hill, okay, say from point B to point C? Well, I could do the energy from point B to point C, or I can do the energy from point A to point C. My energies should be able to be figured out at any given point. And so what I want to do in this case is I think it's easiest just to figure out my energy at A and how much I would lose from B to C due to work and kind of go from there, realizing I'm going to come to stop out here at point C. So I'll show you the whole chart this time and the way I look at the problem and kind of organize my thoughts around it. I look at point A again and realize I only have potential energy there. There's no kinetic and there's no spring. At B, I have the kinetic, okay? And at C, I have no kinetic energy, I have no potential energy due to gravity, and there's no spring that's compressed or stretched to stop me. So where did my energy go, right? Well, it had to go to heat. We have to lose it during the friction here. So my work due to the external force is a loss of all of my energy, either from column A or from column B. I could look at the problem either way. And that work along this level ground would be the negative force of friction, okay, times my displacement, and frictional work will be negative. So I can take a look at my total mechanical energy at A and my total mechanical energy at B and realize that in not just my mechanical energy, but I'm going to have external work out here as well, changing the energy of my system. And so I'm going to lose energy from my system. And so since I'm taking a look at it from the point of view from A to C, I'll lose that frictional work along the path from A to C. So I'm putting that in here as negative, right? And this is the amount of energy I started with. So now, if I solve for this, right, I can set my potential energy equal to my energy of friction. That's the amount of heat that would be transferred, I guess. And then we can keep going. Remember, we're looking for the distance we're sliding along the ground. That's the delta x. So I have to work with my frictional force formula, mu times normal force, right? And we're on a level surface, and we know the normal force would equal gravity, in this case, the weight, okay, the gravitational force. So just substituting in mu times the normal force here and realizing that the normal force is equal to the weight, mg, and substituting in mg for my normal force, look at that, okay? My mass and gravity both cancel. And I come up with an interesting expression for how I can find delta x, the distance I would slide. It's the height divided by mu, okay? Who would think? And mu is stated in the problem to be 0.25. So that means I'll travel 4 times farther than my height, right? So I'll travel a distance of 120 meters before I'd come to a stop. That's a long way. So in reality, mu is probably a bigger number than that. But that's a look at how you could approach that kind of a problem from an energy point of view.